For a bright future, it is essential to efficiently address both our climate and energy challenges. We can only achieve this via a sensible energy transition. Welcome to Key Facts about the journey to our future energy system. I'm your host, Tushar. Before retiring, I led a team that was responsible for providing guidance to the R&D programs in a multinational energy company. I have experience with developing, commercializing, and evaluating technologies in the energy field. Let us start with the definition of a sensible energy transition. It is a transition that deals with all the crucial facts, however inconvenient they might be. Essentially, a sensible energy transition is consistent with both the science and realities. Such a transition requires a framework of energy policies that considers all crucial issues. I'll divide this discussion in four parts: energy transition basics, the requirements for a sustainable energy transition, the key challenges for the transition, and an energy transition framework. In the first part, I'll discuss the energy transition basics. We use a super massive amount of energy globally. For reference, the global amount of energy used is more than the global use of cement, steel, and plastics combined. Currently, fossil fuels provide about 80% of this energy. Climate change is the primary driver of the transition from fossil fuels to low carbon energy. This is different compared to the prior energy transition. The prior transition from biomass to fossil fuels was mainly driven by superior costs and convenience. The energy transition has three main components. One, a shift to low carbon electricity. Two, electrification, which involves the replacement of technologies that use fossil fuels with technologies that use electricity. And three, decarbonization of the difficult applications. The transition will involve many extraordinary changes. I'll discuss a few examples from the Net Zero by 2050 energy transition proposal from the International Energy Agency. Currently, the global production of low carbon electricity is about 12,000 terawatt hours per year. This will need to increase to 77,000 terawatt hours per year. For reference, the total global electricity production per year is only about 30,000 terawatt hours currently. The situation is even more challenging for electrification. Currently, the share of electrification is very low. This is true even for electric cars, which is the most popular example of electrification. At the end of the year 2023, the share of electric cars was less than 4% of the 1.2 billion global cars. Also, the share of buildings that support low carbon emissions is very low. The situation is most challenging for the difficult applications. Decarbonization is currently negligible in this area. The energy transition involves a complete transformation of the energy system. This means a change in how the global society lives, travels, and produces stuff. Expectedly, the change is supermassive. Moreover, the change is desired at a very fast pace. The prior transition took about 100 years. The current transition needs to occur much faster to quickly mitigate the impact from climate change. So we are talking about a super massive change which needs to take place at a very fast pace. Such a transition will only be sustainable if it has a long-term support from the global population. This leads us to the second part, the requirements for a sustainable energy transition. A sensible energy transition must satisfy three main requirements to maintain support from the global population. One, the transition should ensure an adequate access to affordable energy for the global population. Two, the transition should be fair with no undue burden on any country or segment of the population. And three, the transition should efficiently address current and future environmental concerns. This includes decreasing the current and future impacts from climate change, as well as other environmental impacts such as air, water, and land pollution. The energy transition framework must ensure that these requirements are met. This will be crucial to maintain long-term public support. However, there are several challenges to a rapid energy transition, which, if not addressed in the framework, will not allow the requirements to be met. So, to enable success, we must carefully consider all the key challenges. We'll review these next. I have discussed these key challenges in previous episodes. We will only discuss the highlights here. First, we'll consider the challenges associated with the rapid access to the enormous resources that will be required for a rapid energy transition. The crucial resources include critical minerals, investments, land, and skilled workers. Low carbon energy technologies require several times more critical minerals. So, a rapid shift to low carbon technologies will lead to a massive increase in the demand for critical minerals at a very fast pace. The situation will be extreme for certain critical minerals such as lithium, nickel, cobalt, and neodymium. By the year 2030, low carbon technologies alone will need these minerals in quantities that are equivalent or more than the current total global production. Many new mining projects will be required to provide these critical minerals. Recent global data for relevant critical minerals show an average lead time of 20 years for a new mining project. Such projects carry a high financial risk. A rapid energy transition requires rapid access to massive amounts of critical minerals. The very long lead times of new mining projects and high financial risk pose a very serious challenge for such access. Next, let us review the challenge associated with the upfront investments that will be required to shift to low carbon energy. The required global investment for the physical assets alone is estimated to be in the hundreds of trillions of dollars. For reference, the GDP of all the countries in the world combined was roughly $105 trillion in 2023. Massive investments in low carbon energy will be required over the next few decades in all countries across the globe. However, the current annual investments are trillions of dollars lower than that required for a net zero by 2050 energy transition. The investments in low carbon energy technologies will need to increase drastically. However, a rapid access to such massive investments will be very challenging for most countries. Why? Because there are many other crucial issues which compete for the limited funds, and the global debt is increasing rapidly. Examples of competing issues include poverty, healthcare, education, national security, and benefits for senior citizens. Many of these issues lack adequate funding even in advanced economies such as the United States. A rapid access to large investments will be especially difficult for developing countries. United Nations has recently provided data about the magnitude of this problem. Developing nations face an annual investment gap of $2.2 trillion for the energy transition. Typical estimates are based on the physical assets required for the energy transition. They exclude several other costs. The challenge increases when we consider all the associated costs. Access to land resources is another concern. Solar and wind power plants require far more land than fossil fuel power plants. The challenge is not that there is not enough land. The concern is about the practical access to the required land at the desired locations. The solar and wind projects often need to be sited close to the population centers for economic reasons. However, many people are opposed to having such projects close to where they live. Globally, there is an increasing level of such not in my backyard attitude. This is of major concern because the energy transition has large land requirements. New renewables projects and new mines will require vast areas of land. The pushbacks from the local population will make it extremely difficult to get timely access to the required land. Let us review the example of United States. Renewable energy projects have faced significant opposition in 45 states. Over 200 local laws and policies have been issued in 35 states to restrict renewable energy projects. Very few renewable projects have been deployed compared to what is proposed in the future. Even so, the opposition for the projects has been significant. Several times higher deployment is being proposed over the next 3 decades. This will markedly increase the severity of the challenge. Let us discuss the resource challenge of skilled workers next. Tens of millions of skilled workers will be required for the shift to low carbon energy. A shortage of workers is already being observed at the current low levels of deployment. A recent report by the International Energy Agency has captured some of these issues. Europe and United States have a shortage of plumbers, pipe fitters, electricians, heating technicians, and construction workers. China is struggling to fill positions in its factories. Such shortages are already restricting the pace of the shift. Moreover, the shortage of skilled workers in the clean energy area has been rising since the past several years. This challenge is expected to increase in severity as the deployment of low carbon technologies is rapidly ramped up. We'll review the concerns related to global energy security next. Geographical diversity of energy resources is crucial for global energy security. Critical minerals, which are required for low carbon technologies, have a very poor diversity. The top producing country has more than half of the share of the extraction of rare earths, cobalt, lithium, and platinum. The critical minerals require a processing step following their extraction. The processing of critical minerals is even less diverse. China has a dominant share in all aspects. It has a very large share in either the extraction or processing of many critical minerals. Chinese companies have also made major investments in countries such as Australia, Chile, Congo, and Indonesia that produce critical minerals. China also dominates the mass manufacturing of low carbon technologies. China's domination of the entire supply chain is because of its unique conditions, such as access to a cheap and large workforce, the very strong influence of an autocratic government, and access to mineral resources. The dominance of China is alarming. Such dependence on a single country is a major concern for the global energy security. We'll review the technology gaps associated with the energy transition next. The energy transition involves a massive shift to new technologies. For a massive shift, the new technologies must be available for wide global use. This means that each new technology must at least have a comparable performance and cost to the technology it is replacing, and it must not be substantially more expensive. According to the International Energy Agency, the technologies that will be required to reduce about 35% of the CO2 emissions are yet in the demonstration stage. These technologies are not even available in the open market, let alone be competitive. What does history tell us about the time required for a new energy technology to move from a demonstration stage to a significant market share? For wind power, it took over 30 years. For solar power, it took over 50 years. And it took over 30 years for lithium battery use in electric vehicles. The easier technologies such as solar and wind power have taken between 30 to 60 years to reach a modest fraction of the market share. Therefore, most of the difficult technologies are likely to take several decades more to have a major share of the market. This is a major challenge for a rapid energy transition. There is one more major challenge which must be considered: the high risk from future environmental issues related to the energy transition. For this discussion, it is valuable to use fossil fuels as a reference. Nature has provided a massive helping hand to fossil fuels to provide on-demand energy. Specifically, nature has converted the solar energy trapped in dead organisms to high energy density fossil fuels that are available to provide energy as and when needed. The popular low carbon energy options do not have this benefit, as they must deal with their dilute and intermittent energy sources. Consequently, the resource intensity for the low carbon options is markedly higher than that for fossil fuels. A high resource intensity indicates a high level of resource requirements per unit of energy produced. When low carbon options are used in comparable amounts to fossil fuels, they will require extraordinary amounts of resources. This means that the low carbon options have a high risk of severe environmental impact when used at a scale similar to fossil fuels. So, what is required for a sensible energy transition? Basically, we need a framework of sensible policies to drive such a transition. This framework must address all the key challenges we discussed earlier. We will review the highlights of what such a framework of policies might look like. But first, let us revisit the components of the energy transition. The three main components are a shift to low carbon power, electrification, and addressing the difficult to decarbonize applications. Each component has multiple options. For example, consider the many options that are available in the power sector. The number of potential technology options is therefore very large. From a framework viewpoint, there is one crucial question. What should be the strategy to select the appropriate low carbon options? The answer becomes obvious when we consider the key challenges. Recall, there are several major challenges related to the resources. These include the challenges associated with the rapid access to critical minerals, financial investment, land, and skilled workers. Not addressing these resource challenges will lead to massive problems. For example, when the demand outpaces the supply, the access to the required resources will become very difficult. The resulting large rise in costs of the critical minerals, labor, and land will lead to a spike in energy prices. The best way to address these challenges is to ensure that we use the available resources efficiently. This will decrease the stress on the resources and will ensure that there is no spike in costs. To maximize the efficiency of resource use, the policies framework in each country must focus on systematic prioritization between the different energy options. A high priority should be assigned to options that have a high efficiency for greenhouse gas reduction. The policies should support deployment of the options in phases based on prioritization. We are currently in phase 1 of our journey. Policies should mainly support the deployment of the high priority options in each phase. As other options become efficient over the years, they should be given high priority in the later phases. A subsequent phase comes 5 to 10 years after the previous phase. This approach will allow the most efficient use of our resources and enable maximum benefits. There are two useful methods to identify high priority options. In the first method, high priority is assigned to options that are cost effective to reduce greenhouse gases. The focus should be on such options in each phase. Cost effective options are those that have competitive upfront and lifetime costs within each sector. Policies that give top priority to cost-effective options will maximize the impact from the investments. As we discussed earlier, a rapid access to massive investments is a major challenge. All countries have budget limitations. A high priority targeting of cost-effective options will ensure the biggest bang from the available budget, meaning it will ensure the most efficient outcome possible from the investments. I'll first discuss the options that are currently cost-effective to reduce greenhouse gases from the power sector. Utility solar and onshore wind are cost-effective until a certain level of use. The cost-effective level of solar and wind power is likely to be between 10 and 30% in most regions for phase 1. Extending the life of nuclear power plants is very cost-effective. Hydropower and geothermal power are cost-effective when suitable locations are available. Biomass power is cost-effective when low-cost feedstocks are available. New nuclear power is cost-effective in several regions. Short-duration battery storage is cost-effective in certain regions. Natural gas power is cost-effective in regions with low or moderate natural gas prices. These options deserve high priority in the current phase, that is phase 1. What about the cars sector? The current cost-effective options to reduce greenhouse gas emissions from the car sector are mass transit and hybrid cars. Mass transit includes buses, vans, and trains. Mass transit has the lowest upfront and lifetime cost per passenger mile. This is because personal cars require far more vehicle miles when compared to mass transit for the same number of passenger miles. A massive expansion of mass transit must be strongly incentivized over personal cars in densely populated regions. Mass transit also has several other advantages, such as decreasing traffic congestion and increasing the efficiency of resource use. But mass transit by itself is not practical in regions with a low population density. Policies should encourage an expansion of mass transit and the use of hybrid cars in such regions. Hybrid cars have a lower upfront cost than electric cars, are more convenient, and require fewer critical minerals. What about emission reductions from homes? Heat pumps are cost-effective and practical for homes in regions with low carbon electricity and mild climates. Policies should encourage the use of heat pumps in such regions in phase 1. Improvements in insulation should be encouraged for buildings with poor insulation. This is a cost-effective option to lower the energy bills. What about the low carbon options that are not yet cost effective? These technologies should be given high priority in the later phases as they become competitive. Some technologies, such as rooftop solar, are mature but are not cost effective in most regions currently. Subsidies for such options are not an efficient use of our budgets. Until these technologies become cost effective, climate enthusiasts who can afford the extra cost should drive their use. A substantial number of low carbon technologies are not yet mature. For example, the technology options required to reduce 35% of the CO2 in a net zero world are still in the demonstration stages. These low carbon options are geared towards addressing the difficult to decarbonize applications. It will take decades for these options to become cost competitive. Government should increase funding for R&D and early adoption to help these options become cost competitive more quickly. Policies should not give a high priority to widely deploy such options. Energy prices will rise sharply if the global society is forced to use technologies before they are cost competitive. Policies should emphasize the use of these options in a later phase when they become cost competitive. Meanwhile, emission reductions can be obtained for several of these difficult applications by other means. For example, an improvement in fuel efficiency is a cost effective option for decreasing emissions from heavy trucks, ships, and aircraft. Policies should focus on increasing fuel efficiency to decrease emissions until the low carbon options become cost effective. Next, I'll discuss the second method that is useful to identify high priority options. Policies should give high priority to low carbon options in a sequence that maximizes the efficiency of greenhouse gas reduction. Such smart sequencing will decrease the stress on resources such as critical minerals, skilled workers, and land. Recall the wise proverb, do not place the cart before the horse. Smart sequencing avoids the poor use of resources by ensuring that the cart is not placed before the horse. This is especially relevant to electrification. The ability of electrification to reduce greenhouse gases depends on the carbon intensity of the power sector. Lower the carbon intensity, higher is the efficiency of electrification to reduce greenhouse gases. For example, electric cars reduce greenhouse gases by less than 20% in regions where the power sector has a high carbon intensity. So policies should not force a wide use of electrification options until the power sector has achieved a low carbon intensity. Grid limitations are currently a concern for the efficient use of solar and wind power. For example, the limitations lead to curtailment of energy when there is excess local production that cannot be carried to the locations where there is demand. Most importantly, many countries have aging electric grids. Such grids can be easily overwhelmed by poor weather and periodical spikes in electricity demand. So policies must give top priority to increase the reliability of the grid. Giving a high priority to electrification before the electrical grid achieves low carbon intensity and high reliability is not efficient. It is a poor use of the available resources and increases the risk for energy supply disruption. That is why grid upgrades and a low carbon power sector should be given priority over electrification. It is crucial that the global energy supply remains robust. We'll discuss this topic next. There are two major concerns about ensuring a robust global energy supply. The policies framework should address both these concerns. The first concern is about the very poor geographical diversity associated with low carbon energy. Globally, each country will have to deploy massive amounts of low carbon energy technologies every year from now onwards. This will be a continuous process as replacements will be required as the technologies reach end of life. We reviewed earlier how a single country, China, essentially controls the global supply of low carbon energy currently. This will obviously pose a serious energy security risk to the other countries as the world transitions to a low carbon energy system. So policies must focus on improving the geographical diversity. The process will be slow because most countries do not have the unique attributes that China has in terms of low cost resource availability and a massive government influence. So it will take a long time to increase geographical diversity, that is, to develop robust supply chains for low carbon energy technologies across the globe. This highlights the need for adjusting the expectations about the speed of the transition. The second concern is related to the poor assumptions about new oil and gas projects. The scenario analysis by the International Energy Agency is instructive. New oil and gas projects will be required even in their announced pledges scenario, where all the countries meet their aspirational net zero targets. New oil and gas projects are not required only for the net zero by 2050 scenario. There are many unprecedented challenges associated with a net zero by 2050 energy transition. The probability of meeting these challenges is close to zero, meaning net zero by 2050 is not realistic. Unfortunately, many climate activists have an unrealistic optimism about net zero by 2050. They assume that the global society will be able to somehow overcome the many extraordinary challenges. They do not appreciate how unrealistic their assumptions are. Based on such unrealistic assumptions, they are advocating for policies to stop new oil and gas projects. Such wishful thinking is a major concern for the global energy security. It is crucial that the policies related to new fossil fuel projects are based on credible data and not on wishful assumptions. Why? Because restricting fossil fuel production prematurely will cause a major shortage of energy. The energy demand of the global society will not be met, and there will be chaos due to massive spikes in energy costs. To avoid this, policies should not restrict the supply of fossil fuel energy until the energy supply from low carbon technologies is proven to be adequate and affordable. Instead, the focus should be on decreasing the demand for fossil fuels. We can achieve this via policies that incentivize low carbon energy. Next, we'll discuss policies to minimize environmental concerns. A large fraction of the global population is already exposed to a significant impact from climate change. Let us first consider policies which can reduce this impact. Mitigating climate change by decreasing greenhouse gas emissions is a slow process. It cannot help with the impact that the global society is facing today and the future impact which is already baked in. Climate adaptation can provide quick relief from the climate impacts. So climate adaptation should be a major focus along with mitigation. The goal of climate adaptation is to make the global society more resilient to the impact from droughts, floods, heat waves, wildfires, and storms. I will discuss a few examples of climate adaptation below. Drought-resistant farming and maintaining adequate access to water in regions prone to droughts. Building levees and improving water drainage systems in regions prone to flooding. Improving public access to cooling equipment in regions prone to heat waves. Improving assessment and awareness of wildfires. Improving fuel management and land use. Creating buffer zones and fuel breaks, and changing building codes in regions prone to wildfires. Climate adaptation is a very efficient tool to quickly lower the impacts from climate change. So adequate resources must be assigned to climate adaptation. The other concern is the high risk of future environmental side effects from low carbon energy technologies. Recall, low carbon options have a high resource intensity because of the low help from nature. Consequently, they are very likely to have some form of a severe impact on the environment when used at a scale similar to fossil fuels. Policies should use three approaches to address this concern. Policies should focus on using the most diverse set of low carbon options that are possible, meaning all competitive options that are available should be used in each phase. Recall, we discussed a list of cost-effective options earlier for the power sector. All these options should be used in phase 1. The focus should not only be on solar and wind power when other competitive options are also available. For example, nuclear power should be an important option in many countries. This approach is based on the principle that the harmful effect of a substance has a smaller impact when it is used in a dilute form. The use of a diverse set of options will result in a lower share of each technology. This will lead to a lower harmful impact because of the dilution effect. Let us consider the example of fossil fuels as a reference point. The share of fossil fuel energy in the past decades has been about 85%. Its impact of climate change would have been markedly lower if the share had been limited to less than 40%. The second approach is to discourage the waste of energy and encourage options that are energy efficient. This will result in lower use of resources and thereby a lower impact on the environment. For example, policies should strongly incentivize mass transit, that is, buses, rails, and shuttles. Policies should not encourage poor energy habits by giving large incentives to personal cars. Policies should encourage the reduction of food waste. According to United Nations, about a third of all food produced is wasted. The global food sector consumes 30% of the global energy supply and produces 20% of the emissions. So a drastic reduction in food waste can significantly reduce emissions. Policies should ensure that there are timely regulations to limit the environmental impact from the low carbon options. Let us again consider fossil fuels as a reference. If carbon capture and storage and methane leakage had been regulated in a timely manner, the impact from fossil fuels would have been much smaller today. Timely regulations also give adequate time to address the practical issues related to the proposed solutions. So, are the current global energy policies aligned with the proposed framework? Unfortunately, many current policies and proposed paths have a poor alignment. The much needed systematic prioritization is largely missing. Massive subsidies are being used to support poor energy options. Low priority options are being given top priority. Poor policies waste our limited resources on the options that are not effective. This leads to a lower resource availability for the efficient options. I'll discuss a few examples of misalignment. Electric cars do not deserve top priority currently. Nuclear power and short-term battery storage deserves a much higher priority. Yet, the global investment in electric cars has been more than the investment in nuclear power and battery storage combined in recent years. There is a critical need to upgrade the global grids. This should get the highest priority. Yet, the global investment in grids is very low compared to what is required. For example, the investment in grids in the United States alone is short by over $100 billion. Mass transit, which should be a topmost priority option, is not being given high priority. Policies to restrict oil and gas supply and to discourage nuclear power are popular. As we reviewed earlier, such policies are not aligned with the realities on the ground. Why are so many poor policies being promoted? Often, poor policies are promoted because of the assumption that they are the fastest approach to address climate change. But this is a flawed assumption. Poor policies cannot be sustained over the required duration. Why? Because they do not address the key challenges. I'll highlight some crucial concerns. A poor use of our resources can become a major concern for the global debts. A budget discipline is important considering that the global debt is skyrocketing. The global government debt has increased from $22 trillion in 2000 to an incredible $92 trillion in 2022. The total global debt, which includes borrowing by governments, businesses, and households, is over $300 trillion. The energy transition costs are in the hundreds of trillions of dollars. Poor energy policies will greatly increase the costs and lead to a global rise in the global debts. This will make it very painful for the future generations. Poor policies will lead to spike in energy prices, major energy security problems, and will not be able to minimize short and long-term environmental impacts. The climate benefits from poor policies will be low. The public will be exposed to spikes in energy costs and a host of other problems. For example, poor policies will take away resources from efforts related to climate adaptation, addressing poverty, and other crucial problems. The resulting public backlash will delay the energy transition by decades. Using robust policies is the fastest approach to address climate change. It is understandable that a very fast speed is desirable, but poor policies are not the solution. Consider the example of a patient who is suffering from cancer. A robust treatment is available which involves chemotherapy for several weeks followed by a surgery. Trying to speed up the process by forcing all the chemotherapy in a few days will not result in a better outcome. A faster cure is desirable, but moving away from a robust treatment and using a poor treatment will do far more harm than good. Similarly, poor policies will not increase the speed of the transition. Instead, they'll increase the side effects and lead to a poor outcome. A quick recap. A sensible energy transition is crucial to ensure the much needed long term support from the global majority. Such a transition must address the key challenges such as the many resource limitations, energy security concerns, technology gaps, and concerns related to short and long term environmental impacts. A sensible energy transition requires a robust framework of policies. I have discussed the highlights of a possible framework in this episode. The framework of policies has three focus areas. The first focus area is the highly efficient use of resources via systematic prioritization. This involves a focus on cost effective options and smart sequencing in each phase. Options which do not satisfy the criteria should be deployed in a later phase as they become more cost effective and efficient for reducing greenhouse gas emissions. The second focus area is ensuring a robust global energy supply. This involves the geographical diversification of the supply chains of the low carbon technologies and a focus on reducing the demand for fossil fuels as opposed to limiting their supply. The third focus area is to minimize the impact from climate change and other environmental issues. This requires a focus on climate adaptation, use of all competitive low carbon energy options, and timely environmental regulations. Currently, global governments are embracing several poor policies. There is a dangerous misunderstanding that such policies will speed up the transition. But a path involving such poor policies does not address the key challenges of the energy transition and will cause substantial delays. A sensible energy transition, which involves only robust policies, is the fastest path to address our climate and energy challenges. In the interest of time, I have only discussed key highlights in this video. Further details are available in my books.